Welcome to this lecture series in linear algebra. In this lecture, we'll look at the space of all the linear maps between two given vector spaces and endow that with a vector space structure itself. And let us recall what we need. So we certainly need to know what are linear maps, and we need to know this fundamental property of linear maps, that suppose we have two vector spaces V and W over the same base field F, which I have not written. Suppose we fix a basis for the vector space V. Then for any function defined on the set of all the basis vectors mapping into the space W, there is a unique linear extension of F. So formally, there is a unique linear map from V to W which extends F. So this is the inclusion map, meaning it sends V1 to V1, V2 to V2, and so on. And this is our linear map which extends F. So it is behaving the same as F on these vectors, and then on top of that it is a linear map, and there is only one such linear map. So this is a fundamental property that we will use. It's a very simple fact. There is nothing mysterious about this. Alright. So here are the problems for practice. All problems are important. Any problem that I suggest in the problems of my lectures is important, but the ones marked with dagger are especially important. So try to get all of them. Okay. So we will define a vector space structure on this object. So yeah, this notation is the space of all the linear, or the set of all the linear maps from V. Sorry about that. This is the set of all the linear maps from V to W. Okay, so fix vector spaces V and W over the same base field F, and we are going to equip this with the two operations. Of course, since we are trying to make this a vector space, we will be equipping this with two operations. So we just need to prescribe how we add linear maps and how we scale linear maps. Okay. So for two linear maps S and T, going from V to W, we define S plus T as a map from V to W, defined as S plus T of little v is S of V plus T of V for all vectors in little v. So that is how we add linear maps. And for any scalar alpha and any linear map from V to W, we define this thing alpha dot T, or just alpha T, from V to W as via the following recipe. So for each vector V, the output of this on V is the scale of TV by alpha. TV is a vector in W, so it makes sense to scale it by alpha. And that is how we define these things. So one can check that S plus T is a linear map and alpha T is a linear map. So check. S plus T and alpha T are both linear maps from V to W. And further check that this guy is a vector space over F under the operations just discussed. So here the plus, of course, picks two things here and adds them in this way. And by dot we mean the scaling as defined here. We haven't used the dot here, but it is understood. Okay. So this is how we endow this with a vector space structure. And now a natural question arises. If suppose we knew the dimensions of V and W, so as usual, all our vector spaces are assumed to be finite dimensional, even though in this construction it was not used anywhere, but there is no gain we are going to make by dealing with non-finite dimensional vector spaces in this lecture series. So suppose we knew the dimensions of V and W. The question is, can we say something about the dimension of this guy? Is it also finite dimensional? And if yes, then what is its dimension? And the answer to that question is not complicated. The dimension of this vector space is just the product of the dimensions of the individual spaces. It's a very nice result. But the proof is also very easy. We are going to write down the proof in full detail. We're going to write down the proof in full detail, but for the first reading or to get a good idea or to have a good intuition about the proof, it is useful to just take this as a one-dimensional vector space to follow the proof well. Okay, so what we will do is we will fix two bases. So let this be a basis. This is the basis of V, and this is a basis for W. So what we are saying is that dim V is M and dim W is N. Okay, so now we will just write down a basis for this vector space. So for I and J, define the map Tij as the unique linear map satisfying these equations. Okay. So again, why are we defining things this way? This will be clearer once you substitute n equals 1. Okay. So first of all, why does this statement make sense? This makes sense because of what we recalled in the beginning, the fundamental property of linear maps. We have a function on the basis vectors. We have a recipe of how to send basis vectors to vectors in W. And there is a unique linear extension once we have such a recipe. That unique linear extension has been dubbed Ti, j. Okay, so that's that. And let me just note that, just for understanding, that T1, 1 of V1 is 1, but T1, 1 of V2 and so on up to Vm is 0. Okay, this is just a special statement. The general statement has been written above. So our claim is the Tij's form a basis So this, once we prove this, we will be done. So first we will talk about linear independence. So for linear independence, suppose we have scalars where I is in this range and j in that range are such that, or be such that, this summation this is 0. So for linear independence, we want to show that so once we do this orange thing, we will have shown that the list that we see here is indeed linearly independent. Okay, so how do we do this? So fix k. Then zero is equal to this guy. Right? 0 is this, of course, because this is 0. But what is this evaluation? This evaluation is equal to that. So here this is one vector. This is Tij applied to Vk. Let us change the order of summation. And now just use the definition of Tij. So Tij Vk is equal to Wj when I equals k and 0 otherwise. So this summation is nothing but alpha kj wj. That's what it is. And this is 0. Well, this thing is 0. But now the fact that w1 up to wn are a basis means that they are in particular linearly independent, and hence all of these things must be 0. So from the above, or from the thing on the left, we conclude that all of these are 0. Alpha kj is equal to 0 for all j. But k was arbitrary. K was chosen arbitrarily. So each alpha ij is there for 0, and hence we have established linear independence. So you can write that down. And now finally we need to establish the spanning property. So for the spanning property, let T be some arbitrary element in the vector space Hom VW. We want to show that this is in the span of the list that we wrote down. So to see that, just for each I in 1 up to m, we know that there exist scalars. In fact, there exist unique scalars. Alpha I1 up to alpha In, such that TVI is this linear combination. This is simply because this is a vector in the space W, and hence one can write it uniquely as a linear combination of W1 up to Wn. So we have that, and now as an exercise you can just check that T is nothing but that. How do you check this? Well, both are linear maps. This is a linear map and that is a linear map. So to check that they are equal, one just needs to check that they agree on basis vectors. Once they agree on each basis vector, which we have chosen to be v1 up to vm, the two linear maps must also be equal. This is again the same fundamental property that we recalled earlier. So this shows the spanning property also, and hence we have proven that the dimension of this guy is same as the size of this list, but the size of this list is m times n, and hence we have established this theorem. Okay, so that's that. But I want to also offer another perspective, which is essentially the same thing as we did just now, but it is still informative in my opinion. So suppose again we have two vector spaces V and W over a field F, and for the sake of understanding, suppose V is some m-dimensional vector space, but W is for the moment one-dimensional. Okay. So fix a basis for V, and since W is one-dimensional, we have a single, a list of size 1 as a basis for W. So this be a basis for W. Okay. So now here is the thing. For each we know that for each element, so this time the script B is not a list but a set, the set of the vectors that you see here. So for each function from B to W, there is a unique linear extension TF such that this diagram commutes. Again, the fundamental property. This commutes. And another enunciation of the same statement is, for each map phi from B to F, the field F, the base field, there exists T phi from V to W such that something else commutes. Where what is this vertical map? This vertical map just sends alpha to alpha W. Okay? And note that once you think of F as a one-dimensional vector space over the field F itself, this is a linear isomorphism. So once you identify W with F, this triangular thing becomes this square thing is all that is happening. Okay? So we have that. So basically, once you have a map from B to F, you have naturally a map from V to W. That's all we are saying, and therefore we have this, thus we get a map which deserves a very nice color for itself, which I don't have, unfortunately. So thus we get a map theta from this vector space to Hom VW, which sends phi to T phi. Right? And you can show that this is a linear isomorphism. So check that. Interesting exercise. So once you do this, then what is the dimension of this guy? The dimension of this guy is same as the size of B, which is same as the dimension of V. And hence the dimension of this must also be the same as dimension of V, which agrees with what we have stated because the dimension of W is assumed to be 1. So this is one way to prove that theorem. And how do you generalize this when W is an arbitrary finite dimensional vector space? Well, instead of this thing, you will have a direct sum of this thing over, if the dimension of W is n, then you would have an n-fold direct sum here. Think about that, how you would implement the same idea in the general case. So yeah, this is all that I want to say in this lecture. Do not ignore anything. Do not ignore this alternate way. If this looks complicated, that just means that you need to stay on it a little bit longer. Do not ignore such things. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.